Ah! What's the hurry? The kinematics of free fall. So, splash. What happens as objects fall? Well, physicists don't really know why objects fall. We don't really understand what makes gravity happen, but we do know it happens. But we can describe how they fall really accurately using kinematics. As they fall, we know they go faster, and of course that's the definition of acceleration. This means that they accelerate. And they accelerate at a constant rate. The acceleration due to gravity is constant, meaning it changes at a regular rate. So, g is that magic number. G is the shorthand for the acceleration due to gravity. All large objects have a little g value. That's why I sometimes say, I'm the most gravitationally attractive man in the room. Examples, the moon has a gravity of negative 1.67 meters per second squared. That's why astronauts seem to jump so high on the moon. And conversely, Jupiter, one of the largest planets in our solar system, or the largest, has a negative 26 meters per second squared acceleration, almost 3 times that of Earth. Earth, of course, g equals negative 9.81 meters per second squared on the surface of the Earth. So let's use g and figure out what happens as an object falls. Here's a baseball falling from rest. What's its velocity at the end of 1, 2, or 3 seconds? So we can use the kinematics equations that we've learned already, Vf equals Vi plus At, to calculate the velocity at the end of each second. So at the end of 1 second, the velocity will be negative 9.81 meters per second. At the end of 2 seconds, it's now doubled to negative 19.62 meters per second. At the end of 3 seconds, it's reached a velocity of, yeah, you can do the math, negative 29.43 meters per second. Every second, it's getting 9.81 meters per second faster. So let's look at the displacement now. As an object falls, how far has it fallen in that time? We can use the displacement equation, or distance equation, VIT plus 1/2 AT squared, to calculate that. At the end of 1 second, an object's fallen negative 4.09 meters per second. How about 2 seconds? Yeah, go ahead and practice the calculation. It's negative 19.62 meters per second. And at the end of 3 seconds, it's fallen a total distance of 44 meters, negative 44.145. Again, the negative numbers just indicate the direction, the convention that towards the Earth is negative. So if we throw an object downward, let's say we gave it an initial speed of 10 meters per second, and we were going to throw it from the top of a 175-meter tall building. What acceleration does it experience? Well, it experiences the same acceleration. Once it leaves our hand, only gravity can accelerate it towards the Earth. And what's its initial velocity? Negative 10 meters per second. So let's calculate with this number and see what happens. A and VI are in the same direction, so the object will be speeding up. Okay, what's its velocity as it hits the ground, and how long does it take to hit the ground? Using the kinematics, Vf squared equals Vi squared plus 2AD, we can see that the final velocity will be negative 59.4 meters per second as it hits the ground. And we can use kinematics to find out the time, 5.04 seconds. How about throwing something upward? We did this with our rocket lab. Here we have a cannon fired with a shot directly upward from the initial velocity of 50 meters per second. What acceleration does it experience? Well, it's the same, negative 9.81 meters per second squared. And what's its initial velocity? Positive 50 meters per second. So now, VI and A are in opposite directions, which means on the way up, it's going to slow at a rate of negative 9.81 meters per second. See, it's getting slower and slower. The velocity vector is getting smaller and smaller with each second, till of course it reaches its apex. What's the object's velocity as it reaches the top of its flight? Well, at the very top of its flight, for a brief moment of time, all objects temporarily stop and reach a velocity of 0 meters per second. How long does it take the cannonball to reach the top of its flight? Well, we can use kinematics to figure that out. Using the final velocity equation, we can see that it takes 5.1 seconds to reach the top of its flight. What maximum height does it reach? Again, we can use the displacement equation. Figure that out, and we have it reaches a height of 127.4 meters. So kinematics can help us deal with all freefall problems, because freefall is just another kind of acceleration. See ya in class!